good afternoon. So we will continue with our discussion on Gauss-Seidel briefly, and then we will go over to curve fitting. So we will revisit the problem of the chemical reactor. Okay, we solved it just to have a small recap. In the Gauss-Seidel method, we first rearrange the equations such that diagonal dominance is satisfied. Diagonal dominance is aii is greater than the sigma of aij I not equal to j. This is valid for all I, and then you write out x1 equal to b1 minus a1 a12 x2 and so on, and then you dynamically update the latest values of the iterates. So if you do not dynamically update, it is called the Jacobi iteration. So the Gauss-Seidel method is extremely potent, is extremely powerful, and is widely used by all the CFD software. For example, the Fluent, which works on the finite volume method, actually finally you get this variables like u velocity, v velocity, w velocity, temperatures and so on at every grid point, and it is connected to the neighboring grid points using this from your finite volume or finite difference equations. These are simultaneously solved, okay, using the Gauss-Seidel method. Now we will turn around and just see how one can get these equations, okay. So let us say steady state analysis of a series of reactors. Consider 3 reactors, all of which are well stirred. Okay. Consider 3 reactors which are well stirred, and we call these reactors as 1, 2, 3. Now the concentration of the species in each of these reactors is x, let us say milligram per meter cube. These reactors are interconnected by pipes, okay, and we are looking at steady state analysis of a series of reactors. They are all well stirred, so there is a uniform concentration, okay. Now so I have a pipe and I pull out 4 units. So when it is going, it is x, when it is coming, it is y, right. When it is going from here, concentration will be x, when it is coming, it will be y. I am saying that 2x is going from here, 4y, so 2 units are coming from there. So in order, I will just hash this so that you do not get confused, okay. that is 16. So for example this one, what is 2 meter cube per second, x will be milligrams per meter cube. So what are 2? So 2 denotes what? This 2x, it denotes some q or some flow rate. X is basically the concentration multiplied with the flow rate will give you the mass flow rate. Okay. Now if you do a steady state analysis, if you do a steady state mass balance for the 3 reactors 1, 2, 3, you will get 3 equations. There are only 3 variables x, y, z. Please draw a control volume around each of this, do the mass balance and let us see whether you are able to get something. Let us start with reactor 1. So you can just draw a so reactor 1, what do you get? So 2x is going out from here, 4x is going out from here, so minus 6x, 4y is coming inside plus z, minus 4 is equal to 0. Is this the first equation which we got in the last class? Huh?
Yes, sir.
Okay, so after working out this problem, I went back to my office and I did the inverse and I worked out the inverse problem. How should the, so if you pose the problem is how should the 3 reactors be arranged in such a way that you get these 3 equations. Okay, alternatively I could have just said a steady state analysis of series of reactors is shown in the figure. There are 3 reactors well stirred, the concentrations are x, y, z, set up the governing equations for this problem and using the Gauss-Seidel method determine x, y, z. Is that clear? So otherwise it is just like a mathematics class, I mean 4x plus this. Now it is a big puzzle from the equations getting back. I struggled for 2 hours in the last class, but I was trying till I came to the class, it was not working out, so I gave it up. I don't want to give up, so that's why today, okay, 15 minutes we lose on this, but it's worth it. Please check whether you get the other 2 equations. Okay. What happened? You don't want to use these benches or? If there is any small mistake, you let me know. So now you know the goal. We should get the same 3 equations. Varun, are you getting? Got it, right? So what is the second equation?
2x minus 6y plus 3z equal to
2x
minus 6y.
Where is the minus 6y? 2 and 4. Huh?
Plus 3z equal to minus 2.
Is equal to minus 2. Third one.
4x plus y minus 9z equal to minus 16.
Okay, 4x plus y. But this you are not reading out the.
Nice check.
Okay. My is equal to?
Minus 16.
Yeah, that's it. See, the beauty is it should satisfy mass balance, it should also be diagonally dominant. Of course, you can realize that this is not directly lifted from some textbook, right? This is my own problem. So therefore, I struggle to recreate this. So the next year onwards, I will first give this and then ask them to set up the Gauss-Seidel system and then solve it. fine. Now you got an idea of how why Gauss-Seidel method will be useful, or rather I will put it more straight away. Where can you expect linear system of equations in engineering? If you are doing reactor engineering and chemical reaction engineering, all these things, fluidized bed and this thing, fractionating column, petroleum engineering and all these things, you will get this. In fluid flow circuits also you will get. You design the apartment complex, right, the fan, and that is what I have already graded your assignment. For example, there are several branches. Instead of an apartment complex, you are working out the distribution for a city itself. Then there will be places where it is pumped again and so on. And for example, do you know that in Germany nobody has a overhead tank? The water reaches the 5th floor of apartment complexes directly. If you open the tap, it comes. So they have worked backwards and found out how much pressure is required so that water will automatically flow, right. Here it is just above the atmospheric pressure, therefore we have a motor and pump and we build a overhead tank and everything is collected to the overhead tank, and the water comes out with such a high pressure in developed countries that you open the tap, it will automatically come. No, they have unheard of UPS, overhead tanks, all these things are unheard of. They won't know what a German will not understand what a UPS is, because I mean he has never seen a power cut. Okay. Is it uninterrupted or uninterruptible? Uninterrupted. Okay. Fine. So with this we close our discussion on the Gauss-Seidel method. Now we will go to an equally interesting topic, curve fitting. We are talking about authentic and genuine curve fitting, okay. We are not talking about conducting experiments where you first draw the curve and then draw the point. Okay, that is a special category of okay. So this is curve fitting 101, for example. Okay, 101 basically universally a 101 course is the first course. So this is genuine curve fitting 101. Okay, so why curve fitting at all? Why study curve fitting? Why curve fit at all? Why? Why do you want extrapolate? Why can't you keep quiet?
You take data points only for values, you take the experimental values, and for the other you just
forecasting the
extrapolate or interpolate?
Interpolate.
Oh. Why do you want interpolate?
Because you don't want to conduct that many number of
experiments.
Huh? What is the goal of the interpolation?
to come up with an empirical relation.
And do what?
Predict the value.
Write a book. Huh?
For further calculation.
Huh?
For further calculation.
Or what?
In exams.
No, you're all close, but not close enough.
To know the properties of a function at unknown points.
Okay, you want to get the properties of the function at unknown points. For example, if these functions are available only at a known number of points, but you want this function at some other points, that is interpolation. Sometimes extrapolation is also required. For example, you want to do forecasting of demand of a product, forecasting of the monsoon, okay, forecasting of the rainfall, whatever, whether forecasting is in economics or atmospheric science or whatever. Now you need to establish a relationship, right, between the independent variable and the various dependent variables, and you have to prove your hypothesis. That means out of this, suppose your data is collected over 40 years, so you will probably develop a model for 35 or 36 years. Then you will start testing on 37, 38, 39 and 40. If it works, then you say that I have built a model of taking data up to 35 for the first 0 to 35 years, 36 to 40 it is working reasonably well. Therefore, there is no reason why it should misbehave with the 41st year. Therefore, I will start predicting for the 41st, 42nd. That is basically extrapolation or forecasting. Interpolation, oftentimes, for example, thermodynamic properties and so on, they are measured only at some finite values of pressure and temperature, but you want enthalpy, entropy, at other values of pressure and temperature. So you need a method by which you will get these properties. Okay. Therefore, that is only one part of the story. In relation to this course, in relation to this course, why do you want curve fitting?
Because you don't know which point you don't know the exact optimum point. So you find somewhere 2 points before the optimum and after the optimum, and somewhere like once solve already written.
No, even more fundamental than that. For example, when you wanted to do system, when you wanted to get the operating point, what did you start off with?
If you want a model, we will want a
You had a torque speed characteristic of the load, torque speed characteristic of the engine and all that. Who will give you all that? Who will draw those curves for you? Who will give those equations? Nobody will give those equations. People will give you some points, but with these points we cannot hopefully, I mean some optimization techniques will work, discrete optimization and all that, but generally it is more convenient for us to work with functions. Okay. Therefore, the first step in technology is to look at these points and first draw an appropriate function. Okay. That is the best possible function. So already when you are doing curve fitting, some optimization is already inherent in it because you are looking at the best. Now I will tell you the difference between the best and some other curve. For example, if you have got 1000, if you have got some 500 data points, we got some 500 data points, okay, it will be absolutely meaningless for you to have a curve which passes through all the 500 points, because you know that this data, the error is inherent in this data. When error is inherent in this data, then you want to pass a line which gives the minimum deviation from all the points in a least square sense. All that we will explain little later. Therefore, now I have already introduced some more additional concepts to you. Curve fitting does not mean that the curve has to pass through all the points, but there can also be cases when the curve passes through all the points. So in the light of what I have told you just a minute ago, when will you have an exact fit, when will you have an approximate fit? When the number of parameters is less and you have got absolute faith and confidence in your measurements, then go ahead and have an exact fit. But once you have more number of data, then if you are using a polynomial, then the order of the polynomial keeps increasing. What is the basic problem with higher order polynomials? Equation will become bigger, that is okay. Now granted that we can handle complicated equations, the polynomial tends to get very oscillatory, and if you want to work with additional things like derivatives and so on, it will become very, very messy. Therefore, if you are talking about high accuracy data, limited number of data, it is possible for you to go ahead and do exact fit. But if you are dealing with a large number of data points where it is error prone, it is okay to have the best fit. Okay, so already curve fitting can be of two types, best fit and the exact fit. Now for why is curve fitting required at all? So why required? To carry out system simulation and optimization, to determine values of properties, for example. You also want to do what is called a trend analysis. You want to make sense of the data, right? What trend is it following? Is it following an exponential trend, a linear trend? Okay, so to do trend analysis, sometimes, so logical extension is to also do hypothesis testing. For example, it follows some basic model, of economics, it follows some basic model of microbiology, it follows some basic model of fluid mechanics, heat transfer. Whether I have carried out experiments, whether the measurements, if I replot it or draw a curve, whether that hypothesis, whether it is useful for testing that hypothesis, right. So, for hypothesis testing. Whether if you take a course like ME 110, if you plot the marks of all the 800 people, the hypothesis is it will follow a Gaussian distribution. Whether that hypothesis, whether the test is okay, if you do, you can actually plot a curve. Okay. What happens when instead of doing it for the whole class, you do it separately for A batch, B batch, C batch, D batch, okay. Then you split it again dual degree students, and so if you keep on, then you can eventually you can either write a paper or you can go mad to okay. So, in this case I want to test this because central limit theorem says that all data when the number of points becomes too large, it follows the Gaussian normal distribution. So, you can use it for, you can actually plot, draw a curve and check whether it is this thing, find out the two important parameters of the distribution. What are the two important parameters of the Gaussian distribution? Mean and variance. Okay. So, the mean and variance. So, these are the two parameters, two important parameters of the Gaussian distribution. So, if in order to be able to do all this, you need to know curve fitting. Okay. Curve fitting exact and inexact or approximate or best? Okay. So, exact, curve passes through every point. Suitable for small number of parameters. Suitable for large number of parameters. Example. So, H is a function of temperature and pressure. Of course, we didn't use regression in ME 110, that is the thermodynamics. ME 110 is the, now it is called ME 1100, the first course in thermodynamics. There we gave you tables, right, but it is very messy. If you want to write a program, we cannot use tables. So, it is better to convert all these tables into equation form. For example, now software, various kinds of software is available. I mean, you have to just give the temperature and pressure and it will automatically give the enthalpy and all that. All those days of tables and all that are all gone. Okay, but tables are still useful for the classroom environment. That is why we still continue to use that for the first year course at least. Now, if you want something, enthalpy is equal to function of temperature and pressure. So, property data like this, you can go for some exact fit. Calibration data, okay, what is that calibration data? EMF, thermocouple EMF versus temperature, where everything is highly accurate, then you can have an exact fit. Here any regression, example Nusselt number correlation. You consider flow over a cylinder, you heat the cylinder, send cold air, okay, you do experiments under steady state, measure the total amount of heat which is dissipated in order to maintain the cylinder temperature constant, increase the velocity. So, for every Reynolds number find out the heat transfer rate. Heat transfer rate using Newton's law of cooling, convert it to heat transfer coefficient. From heat transfer coefficient get the dimensionless heat transfer coefficient called the Nusselt number. Plot the Nusselt number versus Reynolds number. If you so like, change the fluid from air to water, from water to liquid metals and so on. So, now if you know the correlating variables, for example, the Nusselt number goes as A Reynolds to the power of B, Prandtl to the power of C. If you have sufficient number of data, it is possible for you to get A, B, C from experiments. Okay. Now, why required to carry out on all this? Okay. The basis for all this is calculations regardless of whether you do calculations or experiments, you get values only at discrete number of points, correct? However, my idea of doing experiments and calculations is not just to get values at discrete number of experiments. I know that as a scientist, if I do the experiment carefully, I will get some 5 values of Nusselt number for 5 values of Reynolds number, but I am not going to stop there. I am going to have a predictive relationship like this, which I can use for optimizing the whole system and so on. I want to do system simulation and then I want to do optimization. I am not just satisfied with trying to find how the heat transfer varies with Reynolds number. That is 101 kind of thing, but I want to do more. I want to do system simulation optimization, but this is the limitation I have. Therefore, there is an intermediate step which is involved, which requires you to convert all this into an equation form, which can be played around with and you can use your simulation and optimization. Is that okay? So, this gives you a broad overview of the widely used classification, namely exact fit and best fit. In the rest of today's class, we will look at some possibilities of exact fits and we will also solve problems. Polynomial interpolation, Lagrange interpolation, Newton's divided difference polynomial, then you have spline fit. The exact fit can also be called as interpolation. Okay. Let us start with A. So, I propose that y varies quadratically with x. Okay. So, I write the relationship as y equal to a naught plus a1 x plus a2 x square, a naught, a1, a2 are the 3 constants. So, in order to get 3 constants, I need the values of y at how many values of x? 3 values. Okay. So, so it will exactly satisfy there will be no error when you apply this formula at x naught, x1 and x2, but there will be some error when you apply it in between x naught, x1 and x2, correct, because we are approximating the whole physics by a, we are approximating the physics by a quadratic. Okay. You can only force with 3 points you can draw a parabola, I mean you can draw a quadratic, you can make a quadratic pass through, you can only do that much, every point in between you cannot force, okay, because after all you are representing some physics, right. Let us start off, let us have a warm up. So, problem number 18 is it? 14. Evaluate the natural logarithm of 5. Problem number 14. We will start off with some simple mathematical problems, then we will go to a thermal system problem. Evaluate the natural logarithm of 5. Evaluate the natural logarithm of 5 using quadratic interpolation. Evaluate the natural logarithm of 5 using quadratic interpolation given please report the error, the exact value you can get from the calculator. Vinay, what is the problem? Is it 2 point, what is it?
Correct one is ln 3.
No, there is a mistake there. What is ln 7?
Ln 3 is 1.09.
I don't want ln 3. What is ln 7?
Ln 7 is correct. Ln 3 is wrong. 1.09.
Yeah, it's a mistake. Okay. Yeah, it's a small typo. Anyway, what is ln 5? Huh? But what do you get? You will not get the same. So, what do you get? Minus
1.747569854431.
Okay. 1.099, right? So x is 1, right? Is correct, right?
Yeah. That's it.
So A naught is minus point, correct? Okay, A1
minus point
0.05, that's it. So linear interpolation you have done in thermodynamics, right? Polynomial interpolation maybe is not new to you, or it's not very difficult, but now if you do, therefore y is equal to minus seven
1.609. 9.17.
9. It depends on how you. Percentage error 9. Okay. This is a simple example. It demonstrates. It lets you understand how this works. Of course, you can complicate it by having cubic. If you have 8 points, you can have a 7th degree polynomial and all that. But what happens is beyond a cubic, then the polynomial tends to get highly oscillatory. It is not advisable. Okay, you might rather go in for what is called a cubic spline or a quadratic spline, where locally 3 points you will fit with a lower order curve, so that you generally get a smooth curve. Okay, so if you have a highly accurate calibration data, thermocouple data, EMF versus temperature and so on, then you can use this, right? The next one I am going to teach you is the most powerful Lagrange interpolating polynomial. So I will start with the second order Lagrange interpolating polynomial. For example, if you have you know that you can use the interpolating polynomial which you just studied now, the polynomial interpolation for this, but the Lagrangian polynomial is much more what shall I say, it is much more potent in the sense that it can be easily extended to any number of points. It is easier for you to take the first derivative, second derivative and so on, and much of the, I mean, for example, the post processing of CFD work and so on, after we get the velocities and temperatures, we in fact left, right and center, we all use the Lagrange interpolating polynomial to get the gradient of temperature and the gradient of velocity. Once you get the gradient of temperature, we can multiply with thermal conductivity to get the Q. From Q, using Newton's law, we can get H. From H, we can get Nusselt number, then we can correlate for Nusselt number and so on. So it is ideal for post processing. So what is this Lagrange interpolating formula? Okay. So given x0, x1, x2 they can be unequally spaced, there is no need that they have to be equally spaced, and corresponding values of the dependent variable are y0, y1 and y2. The Lagrange polynomial is like this: y the Lagrange interpolating formula. This is called the Lagrange interpolating polynomial order 2. So you start with this, suppose you are looking at this, so you do x minus x1 and x minus x2 divided by x0 minus x1 x0 minus x2 into y0 plus x minus x0 and x minus x2 divided by x1 minus x0 x1 minus x2 into y1 and so on. That is the way you do, right. Can we write this in compact mathematical form? Can you try? Y phi of x x minus xj, okay, divided by here j is equal to that pi is for multiplication. For people who are unfamiliar, that pi is the mathematical this thing for multiplication. So this can be written in a succinct or a compact form like this. Okay, so it is possible for you to get first derivative, second derivative. It's possible for you. The first derivative will still be a function of x. The second derivative will be a constant, right? The second derivative will not be a function of x and so on. This is for a second order polynomial. You can go up to a third order polynomial where you can take y0, y1, y2 and y3. Okay. In the next class we can solve a heat transfer problem with the Lagrange interpolation formula, alright, and then we will go on to Newton's, divided difference polynomial, and then we have to round it off with the cubic spline. Okay.